Conservation of momentum. Helicopters. I'm going to draw the basic classic helicopter. And it looks a lot like a whale when I do it.
Oh, she does.
It's supposed to be a helicopter. All right, so I got a helicopter sitting on the pad, helipad, whatever it's called, sitting on the concrete, getting ready to take off. When it gets ready to take off, it starts the blade right here. It starts it whirling. Well, in order to get this blade to turn, something has to push it. If something is pushing that blade one direction, the blade's pushing back. That's Newton's third law. And so whatever is attached, so whatever is pushing the blade to turn around, that is pushing back to try to get the helicopter to turn around in the other direction. Because as it starts, there's no angular momentum, and so when it starts to go, this will have angular momentum in one direction, this will have angular momentum in the other. So if the blade is spinning around like that, the helicopter wants to spin around the other way. Now the way that they solve this is they put another blade on the tail blowing around the other way. If you've seen the movies where they shoot out the back rotor or something goes wrong and suddenly the helicopter starts spinning around, that's what's happening. Is you got rid of the blade, you got rid of this back blade, which is keeping the helicopter aligned. Now there's two other designs of helicopters which basically tried to resolve this problem. Two that I know of. There is the double blade. So let me draw my whale again. Where the blades are moving in opposite directions. Now they're tilted so that they're all blowing air down to lift the helicopter, but to get blades turning in both directions, wow, that required some more coordination than what I just showed just then. So one's going around this way, one's going that way, so.
Just go ahead, Mr.
Something like that. You can work on it on your own. And the other one is the Chinook, where you have a blade here and a blade over here. So this one, if this spins, it's trying to send the helicopter one direction. This one is trying to send the helicopter the opposite way, and it balances out.
Is it the same with the airplanes? Have you heard of the Wright brothers?
I've heard the right one.
What? Why is everybody laughing?
Because we all learned about that.
Oh, well, I'm from Florida, so I don't know why. I just went to the museum this past weekend and saw that. It was pretty cool how they built the plane and they showed him on it, using his hips to move it. Y'all know that, but
I didn't know that, sis. I didn't know that.
Well, there's a lot of physics involved, so I figured that's pretty cool.
It is. I haven't seen an exhibit. I just the first in flight has been drilled into me for so long.
Yeah. Well, they have it set up to show how far and with the physics that they did. It shows their blueprint and all that stuff. It's pretty cool. And they showed outside how far each three of them got. And I thought Wilburn was the farthest. He got the farthest.
Were those the guys who knew that they may crash, or they just always had extra stuff? That they would crash and be ready to build back again or something like that?
I would not be surprised.
I don't know.
There's that whole Kitty Hawk thing.
Yeah.
Their plane, I'm pretty sure, did have propellers that spin in opposite directions. So
Yeah, it did.
I guess
It
they're
has
thinking
it
ahead.
on there.
I would be surprised that it would be light enough that would be an issue, but I guess you're not taking any chances potentially.
Well, I have a picture of it. You wanna look at it?
I am curious right now. Excuse me.
Here. Well, that's it, but I can't really tell, but you can see in the middle where it has that, and then also the motor's not in it because they crashed it and broke it. So.
Yes, I think those is the guys.
But I think that's the top of it. Here, it shows it in a regular view. Like a little metal one.
I'm trying to see if there's the
You
propellers.
look at it, you know it.
Thank you.
If you slide, there's the metal. That's a little tiny thing of it.
I guess those are propellers up there. Is that a propeller?
I don't know. Maybe. I don't know. 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 I don't know That's like the elevator here.
Alright.
There, I think that's it right there in the back. That's the back of it. So they only have one in the back actually.
Okay.
I think.
There might be one on the other side of that thing, but, alright, thank you. Alright, so we've talked about circular motion here. Let's take another application. I'm officially done with 8. So in terms of what you can do at home, we're not having a quiz on 8 by itself. But you can start working on the homework problems. And that way, next time you come in and ask questions on if there's something I missed. But now let's get to outer space. So first we're gonna start out with just gravitational force. And then that will lead into orbits and black holes and other such things. So far we have dealt with the force due to gravity being weight because we've only dealt with objects relatively small compared to the planet or moon near the surface of the planet or moon. But now we can become more general. So the question I'm going to ask you is, upon what does the force due to gravity depend? Based on your gut feeling.
Where you standing? Where you standing at?
So where am I? What?
You said, what does it depend on? It depends on where your location is?
Okay. So location would be one thing, so that distance.
Okay.
So the farther you are away, the more gravitational pull, or the farther you are away, the less gravitational pull?
Less.
All right, so that's gonna go on the bottom.
Is it also based on the size of the planet?
Not the size,
Mass?
the mass. So mass of the planet, so I got its mass there. Obviously I left space for other things.
What's the R again?
The distance, it would actually end up being center to center distance. Or center of mass to center of mass distance. But remember that I should be able to flip things and get the exact same answer. So yes, there's a gravitational pull between me and the Earth. I am being pulled down with 220 pounds of force, or somewhere around there. But I'm also pulling up on the Earth with 220 pounds of force. Now, because how massive the Earth is, it doesn't get affected by it as much as I am. But it does require 2 masses. And I should be able to flip them and get the exact same answer. Well, the only 2 math operations that we've dealt with so far where I can just flip 2 things and get the same answer are addition and multiplication. You happen to be multiplying here. So the bigger the mass, either of the masses, the greater the force. I need to make one small adjustment here. I can't justify it. It was actually originally found experimentally. There are people who are trying to figure out whether this is actually the right number I'm about to write down, but this should be squared. Now, it seems like a simple matter, but there are people who are trying to figure out, is that really 2 or is that 2.00001?
What
What's
is
the
that?
other M for,
Yeah,
Mr.?
that's what.
Because there are 2 masses involved. Gravitational force requires 2 masses, and those are the 2 masses.
Okay,
We're gonna do a plug and chug in just a moment.
all right.
And notice I did leave a space up front. The last space deals with what units you're working in. In international standard units, this value up front, this big G right here is known as the gravitational constant. I'm going to put in parentheses here, universal. But some sources might still call it the universal gravitational constant. That sort of fell out of favor sometime within my lifetime, because we know what the value is here. We don't necessarily know if it's the exact same value in another galaxy. We have no reason to think it's not, but we don't know for sure.
Is that on the book uses D instead of, R.
Oh, yeah, he likes using D. R is what I'm used to.
Would D mean diameter?
Distance.
Oh, I knew that.
Now, the value of this constant, unlike acceleration due to gravity, little g is not a constant. We pretend it is way too much, but it's not a constant. The gravitational constant is a constant as far as we're concerned. 6.67 times 10 to the negative 11th, and then the units, Newton meter squared per kilogram squared.
So that's the formula right there, Phil?
That is the value of that.
Value.
Not a formula, just, that's the number.
Like 9.8 is the value of.
Did you stop mid-sentence?
Yeah, I fell asleep.
Good one.
Okay.
Like a score is 20,
Yeah,
gravitational constant is this with units. And so if you're working in international standard units, which we are, this is the number that you're gonna use. This does mean that on your calculator, you need to know how to do the exponents. You need to know how to deal with the times 10 to the negative 11. Seeing way too many students, I will tell you that there will be at least one problem on the quiz that requires you to be able to have to do this. If you do not have your calculator here, when we do the problem, make sure you write it down and you try it at home. All right, so this formula right here, it's an attractive force, so they're trying to pull things together. It's between any two masses. So I'm gonna do right now a crude approximation of the gravitational force between me and the textbook that's sitting on the table right there. So my mass is about 100 kilograms, as I've said more than once. The other mass, and it doesn't matter which one's mass 1 and mass 2, you're multiplying them. The other mass is, I'm gonna say, 1.2 kilograms. For illustrative purposes, it's good enough. Now the distance matters. There's a greater gravitational pull between us now than when I walk over here. So I'm just gonna set it so when I was here, that's about 1.5 meters away-ish. So R, or D from the book's point of view, 1.5 meters. So the gravitational pull between us is 6.67 times 10 to the negative 11th times 100 times 1.2 divided by 1.5 squared. And if someone would be kind enough.
I wish I knew how to do that. How do you get to the 11th power to the negative 11th?
All right, so on the calculator, depending on the one that you have, but you would typically hit 6.67, and then there's an E button or an EE button,
Yeah.
and then you hit that button and then type in negative 11.
See, you know I'm a little slow. 6.67. You said that one?
And then that button,
So,
that EE, and then type in negative 11 or 11 negative.
that's it?
That's 6.67 times 10 to the negative 11.
Shut up. Okay.
And then times 100 times 1.2 divided by
Do I
1.5
hit
squared.
equal?
Pardon?
Do I hit equal?
No, that's just like you would type in a normal number, that's, you typed in that number, times 10, or times 100.
So you do the times the 10, then you hit the E button, then do 11, the negative 11.
Depends. All right, this is where some students mess up. Do you have an answer?
Yeah.
Okay.
So this right here, that's what I did.
I wonder if that's the answer.
Oh, is that E? Yeah, you definitely do not want E.
Oh, I thought you said E.
So it's,
I'm not reading.
EE, see the blue right there, it says EE.
So what do I do, hit that first?
Yep, and then type in negative 11.
You got what?
Oh.
Oh my
All right,
goodness.
get rid of the,
Okay, give me
no,
try again. I guess I'm.
get rid of the multiplication symbol too. All right, so you have 6.67, then hit E,
One of them gives me a -8 and one
and
of them
negative 11. Or 11 negative, I don't know, all right, that is the root number, that's 6.67 times 10 to the negative 11.
So you don't, I don't need a 10 because it's
No.
already there.
Yeah, that's what the EE represents times 10 to the. All right, Rebecca, what did you get?
You said it's not supposed to have an E in it, right? Like the final answer?
If you, oh, the final answer might.
Okay, I got 3.5573.
How do you got all that?
I don't know if it's right.
Times,
Ew.
you had you had EE in it? You just had 3.573?
Yeah, it's like 3 repeating for a while and then E -9.
Okay. Times 10 to the negative 9. That's what that EE step represents.
Okay.
I didn't get that at all.
All right, what did you get?
8.004 e to the -9.
Mister, are we supposed to be multiplying all of that and then dividing it by 1.5?
1.5
So, I
squared.
did forget to divide, so that's it.
1.5 squared.
Also, it's 0.5573. You're missing a 5 in it.
Thank you.
What'd you get? I just got a bunch of zeros and then a 4.
Me too, yeah.
All right, so this comes down to what your calculator displays.
Oh, and
So-
and do the parentheses first.
That's
We
what
needed
I
to do
did.
that.
Not necessarily, you might actually have the right answer, but your calculator just doesn't want to display it in a convenient way. So this right here, this is, I'm about to jump into the next bit. What are the units?
We got, kilograms, meters per
Used
second.
to be meters per second because it's gravity.
Think about what we're trying to find.
You said center of gravity, right? Or what was it that you said? I can't remember
Gravitational.
what you said.
Oh, Lord.
We're trying to find the gravitational force.
That's what I meant.
What are the
I
units?
didn't want to finish saying it.
Is
come
it
back with
newtons?
that.
Yeah, Newton,
Meters,
just Newton.
newtons.
Yeah, my calculator is just being done.
All right, so where do I think the calculator's, what it's doing? So this is scientific notation. I can get rid of this time 10 to the negative by moving the decimal point. So if it's a negative here, I'm gonna move the decimal point off to the left. So it'd be 0.0000003557 newtons. That is written out for me, and I suspect your calculator is doing that.
Yeah.
And so it rounded off
The 4.
to a 4 there.
Mm.
I have a question. Okay, so I did it 2 different ways. One way I did it with the EE, and the other way I did it with the little triangle thing.
All right, oh, did you do,
When you do like 10 to the, so one way I use this thing, and I get a -9, but when I
We were
choose,
leaving soon. Yeah. There's like 20 minutes left.
Thank you.
Have a good one.
I'd have to see more of what's going on there, I'm not 100% sure. What I've seen some students do, and this is not, do not do this, so Mr. Young. Just off to the side. 6.67 times 10 e -11. I didn't see you did that, but I have sometimes seen students do this. This right here is already a times 10 to the -11th, so this is 6.67 times 10 times 10 to the -11th. So you got an extra value, an extra 10 in there that doesn't belong. This is not correct. So it's either gonna be 6.67 e -11 or 6.67 times 10 raised to the -11. So, and I'm not quite sure why you were getting,
so I have to do them so you can see, like this one has little hat things, negative
Yeah.
ones, and then this one has the EE, and you come out with one different exponent.
oh, this is, you have an extra 10 there, because you did that. It's only displaying one of the e's here,
Oh,
but you did times 10 times 10 to the negative 11th.
oh, so I wouldn't put the 10, I would just put the E.
Right, right.
Okay, I see. Gotcha.
Hitting the E button takes the place of
Of the 10.
typing this in.
Got it.
So mister, if we got all of those zeros and 4, we did it right, you said?
Yeah, if there are 8 zeros and then a 4.
How many I've got?
I did eight.
Okay. Cause
Um,
I was doing it a lot of times and it just kept giving me that, but it didn't give me, I didn't see that over there.
you added that
Yep.
too.
Touche.
Okay.
All right, so, a couple points here. One, that's a tiny number. This is why when we did force diagrams, we ignored the gravitational forces between the small masses. It is tiny, and the only people who care about this are people who do gravitational studies. I did not when I was working on my dissertation. To give you an idea, the people who do gravitational studies, there was a study that was being done on gravitational forces. And they were getting different values in the spring than they were in the fall. And they couldn't quite figure it out, it took them a while before they figured out what was actually going on. The room where they were doing the experiment was in the basement. In the spring, it rained more, and enough water soaked into the hill on the other side of the wall that it affected their experiments in the spring. It didn't rain as much in the fall, and so it was drier, and that gravitational pull from the water was not affecting it as much. Those are the people who care about those things. I was just smashing stuff.
So, if we got, I guess, all the zeros and 4, how does she get zeros and 3, 5, 5, 7, 3, 1?
Oh, cause they're.
If the calculator gave it to you in scientific notation, you would get that.
Okay,
And so if your calculator didn't give it to you in scientific notation, then it's gonna round off at some place.
okay.
If our calculator gives us the one that has like all the zeros, and we put that like 0.3 or 0.4, it's rounded up, times 10 to the negative 9, would that still be counted as incorrect because we rounded, because our calculator did?
All right, ideally, no.